So my name is Wang. I'm a fourth-year PhD student working for RISE. So I would like to present the work we done in ARCADIAN-IoT, which is about federated learning, and the name is Federated AI for cybersecurity. So first, I would like to go through the outline for this presentation. First, as Valentina have been introducing a little bit about federated learning, and now we'll also have the high-level introduction of it. And second, I will start with the challenges of this federated learning, and what have we implement and development in ARCADIAN-IoT. And we mainly focus on the model resizing and sharing, which is we call SmartFA. And finally, we have the conclusion, which is the final considerations. So first of all, what is federated learning? It's actually because of GDPR, people don't want to share their private data with the central cloud. So that's why we have as people start to have this topic. This federated learning actually is a distributed machine learning approach that can enable the multiple clients to collaboratively train the model in a decentralized way, but they don't need to share their data, so the data will stay on their devices. So this is actually introduced by the McMahon in 2017, which is implemented in Google Keyboard, which means that the user of the keyboard can have their own user preferences. They have the personal model on their devices, but they don't really show their behavior to the central cloud. So I would like to draw your attention to what is actually doing in the federated learning. So first of all, they have the model is initialized in the central cloud, and they deploy it to the multiple clients, and they have their own local training on the devices with their local data set. And the last step is the server will calls for the aggregation for every client to send by the updates or the models. So that is one round of the iteration of training in federated learning. It seems quite perfect, but still they have some challenges that is because it is quite new, it is still immature. So they still cause many challenges we need to address. That's also for the researcher in this area to looking for. Because for example, first of all, if you can imagine that many clients needs to communicate with the central clouds, they need to download the initialize the models at the first time, and then they need to update the model every time in every iteration. So this will cause a lot of the communication overhead. That depends on the different model size, it will be worse. You also have some communication delay. And as you can imagine, because the different clients may have different systems, so the heterogeneity of the system also can have some problem that cause some different, that also have the consequence to the statistical heterogeneity. Because of the data on each devices, there will be some problem that will cause the data distribution to be non-independent and analytical. And especially in security area, we usually have the intrusion detection system, we have the nominative traffic, and we have benign traffic. The data could be really imbalanced because we may have more benign traffic than the nominative traffic. So there also will be some problem in this area. So for security and privacy issues in federated learning, first of all, we can think about is what if the cloud, the server, central cloud server is malicious, is compromised. Then they will have the problem that the model can be compromised as well. So it will also affect a whole learning process. And the second situation that will be, what if the one of the clients is compromised? Then you will also can corrupt all the learning process of the federated learning, and will also affect the other clients in the server. The third situation would be, what if there is one eavesdropper in the middle of the communication that can do some adversary behavior. So from a security aspect, they already have a lot of discussion on this aspect. Like we have this data or model policing attack, or we can call it backdoor. There's one kind of the target attack that's called backdoor. And they may have the model inversion attack, which means usually is happened on the cloud, the aggregator can invert the model based on the model updates or the updated models. So this will have some security problems actually. Second, that it will be the privacy attack. Like even they don't share data, this still possible that the adversary can influence the members, like a membership of this the training data set. So this will cause the privacy attack. But in this presentation, we are not, because there's a lot of the adversary attacks, I will not go through everything, but I will focus more on the poisoning attack. So I would like to discuss more what is poisoning attack. So poisoning attack is like one adversary, they can add in noise to the training data set. For example, you can see the left-hand side is a figure that is classified, it should be classified as panda, and it's with 57.7 confidence. But adversary added a noise to this image, then make the classifier classify this image to the goblin. It will can have 99.3 confidence. So it's it could the classifier can misclassify this kind of data. That's what we call the poisoning attack in general. And what is backdoor attack is target attack of poisoning attack. Usually they inject the trigger, which is like a red square here, to the images or data. It can say like that noise. And this is a figure from, this red square could be the dog's features that makes these cat's figures, that classified it to the dog that is in training phase. So when they infer, the model is in the inference phase, the cat can be with the trigger that can be classified as a dog. So that is we call that backdoor attack. So besides of machine learning solutions, they still have some defense technique that can be implemented in a security way, a security area. So for example, differential privacy, that is actually adding some noise to max the influence of the client or model that can prevent the model be influenced. And they have the security multi-party computation that actually can also add additional communication around to max the actual model updates. And they have, of course, you can encrypt your model by homomorphic encryption, and they may have some other hybrid protocols that is introduced to defend against this kind of adversary. So what we have done in ARCADIAN-IoT mainly focus on the machine learning techniques to defend against this kind of problem and attacks. So what is a component in this ARCADIAN-IoT? We actually built up some different modules. First of all, we have data rebalancer. This is actually, we will not go through it too much in this presentation, but actually we have built up this data rebalancer to address the non-IID and imbalanced data. That is, we provide a way to rebalance the data to fit it to the framework. And secondly, we have this sparse spot. This actually about the model resizing and sharing. It's actually we provide a communication efficient and robust framework for the model aggregation. So the data rebalancer will not it's nothing to do with the model. It's only touch the data, and we only generate something in the data to help the others to rebalance their own data set. And Sparsify will not touch the data. They only have the way to tackle the problem with the model sharing problem. So in this presentation, I would like to go to some details about this model resizing and sharing. We call this Sparsify, and this work has been published in the journal Computer and Security Journal, published in this year. So the motivation of this paper or of this work, things I have already mentioned previously. So standard fair cost massive communication overhead, uploading, downloading the models, and updating the models weight. This will cause a lot of communication overhead. And typical federal aggregation rule, such as federal averaging, is vulnerable to those attacks because it is first actually federal averaging is the first aggregation rule proposed in 2017. There is no too much detail about the rosary attacks. So that's why we start this topic. So idea is that what if we don't need the central cloud to coordinate the federal learning or coordinate the learning task? We only have the peers to talk to each other. So we call it peer-to-peer federal learning. There is no central cloud, so which means we can reduce amount of the communication between the different central server and the clients. Each client only talks to its connected peers. So for example, this guy doesn't talk to the one here, but this guy will talk to the others clients at the same time. So they will somehow reduce the amount of the communication. And we try to resize the shared model we propose a model responsification technique to isolate the communication. I will talk about it in the following slides. And we also propose a robust federal aggregation rule to defend against other rosary attacks, which means I will also talk more on this. So that is a goal of this work. So so the architecture could be like this. We have two main sub models, which is for communication efficiency. The second one is for the robustness. The first model I call it specifier, and the second one could tone tuner. So as you can see the right hand side of the figure, for example, we have 3 clients. Each client have their own data set on the devices or on the server, on the client. So this we are applying this to the IDS problem, intrusion detection system problem. So they train their own local model here, and then before they share their own model to the clients, the model will be specified by the specifier we propose here in this work. And then when the others, for example, C2 receive the models contribute by the C1, you will not go directly to the own model. You will go through the tuner, which is the second part of the model that we contribute. This tuner will tune the weight of the peers, the connected peers. They will control the amount of the contribution to its peers. So that is about the whole architecture on this. So I will go through each one more in detail. So what is a model sophistication? Actually, that is the you can think about there's the model weights that is shared between each peers. It could be very big, but here I only say it's like 5 by 5 5 by 5 matrix, but it could be really big. It depends on what is the model size. And then we do the Hammered product with a mask. That's only, so you can see the because like most of the weights are zero out. So only 1, 2, 3, 4, 5 weights here are going to share with its peers. So so at this moment, they already have some papers around these topics. They propose some different techniques or different tactics to how do we share how do we specify the model. So for example, the first one is random case specification. So random case specification, which means it's randomly generated mask with k weights that is being maxed. So the second one is top case specification is more advanced because they max the k weights with the largest magnitude in the gradient. So, but still, it is not really practical because it still can somehow some weights that have the largest magnitude that still contributing to the peers. Some weights that's never going to be shared with the peers, so they will actually have some problems. So what we propose is we add a momentum to the top K specification. Then what we do is we improve it, and then actually can stabilize the training. I cannot go too much in detail because of time. So if you have any questions, just can ask me after this presentation. So that is about the specification. And then we have this weight tuning that is actually for the robustness. And this tuner is actually try to tune every peer's weight. So what is peer's weight? For example, you can see this figure. Maybe we have 5 clients here, and 1 client is compromised devices, and each guy needs to try. Of course, if the benign one don't want to get updates by these adversaries. So every client will assign the weight to the peers that can control the contribution of each peers. Then that's actually how to assign the weight is actually based on 5 metrics. First of all is data size. Data size, which means how many data of the clients have, and data variance of these peers, and then how much connectivity to this peer. We assume that the peer who connected to more others peers that is more important than the others peers. So that is what we assume, that more connectivity, the connectivity is higher than the score for this should be better. And the model similarity. So we will calculate the model similarity between its own local model and the models updated by the other peers. And also we consider the model divergence, which means we also see whether it has there is what diverge between each others, how much diverge, and it may cause some problem if we take the model updates by this compromised client. So after we have these 5 metrics, when we tune the peers weight by utilizing Bayesian optimization, and it is a probabilistic model that we can have the best, the optimal combination of these 5 metrics. So in general, the workflow of this work is actually we have the cloud, but this only for initialize the model, because every client has to be the same structure of the model. Then the cloud, after that, the cloud will be just leave alone, like just stay there. And then we have the other clients that will start with the learning processes. Then we had the weight, and we specify the weight, and then the sparse weight will send to the other clients to the tuner model, and tuner model will update the main model. So this will be like this workflow. So finally, I would like to share some results of this work. So we try to evaluate how good the specifier can defend against the adversarial attacks. So there are 4 adversarial attacks that we are actually experiment with. So one is label flipping attacks. That is the attack proposed by the previous paper. This actually it's like a noise, like a pointing attack that they flip the label from benign to anomaly and to anomaly to benign. So they flip the label that's like a pointing attack. Noise attack is what we discussed about this. They add the noise to the data. It's quite naive. And objective function pointing attack is we have developed in this work that we reverse the objective function from minimize loss to maximize loss. And we had the Byzantine attack. It is quite powerful, and many papers have discussed this Byzantine robust federated learning aggregation. So that's why we have this Byzantine attack, which is about when malicious clients send arbitrary updates to the others, then will cause all the learning process being corrupt. So there are 4 attacks we are going to talk about, and we test 2 data sets. One is mainly about anomaly detection, so they only have anomaly and benign traffic. Then it's about network traffic flow data. One is MBIoT, that is the online available data set, and there's another one called UNSW.IoT, that is a data set which is really imbalanced. So we used our data rebalancer techniques to rebalance the data set of this. So I will show the result combination with our data rebalancer. So first of all, I would like to share our communication result. The communication result we compare with federated averaging, which means there's no there's no sparsification any technique applied. And we have random K Random K is the random case classification, and we have top K classification, and we have our own work, which is without any tuner involved. So as you can see from the AUC and the F1 score, you can see that red line represent our work and can perform the best in this case. But still, compared to if you share every weight of the model, you can get the best performance. So that's why federal averaging can have the better performance. But momentum top take can have the second good. That because we specify that we also make the model communicate more easily. So for robustness result, we have the 3 scenarios with 5 clients and 1 with the adversary with scenarios, 3 classic scenarios, which involves complete graph, incomplete graph, and chain. Complete graph is everyone connected to each other. Incomplete graph is like more like more like a sensor network, like not every player is connected to each other's. And chain is like a chain, like everyone only connect to 1 or 2 peers. So as you can see, we compare with other baselines, and specified is our method, and we can see that our method for every FS score and false negative rate, it can get the best performance. And we also try with a random network topology, which means it's all incomplete graph, but it's randomly adjacent with each different each other. So we are not controlling anything. Then we test with 10 clients, 1 with adversary involved, and 20 clients with serial adversary involved. And we can see that actually from the 2 data points in attack, or you can see from everything that the model, there's not too much differences between the performance of these different baselines, because actually we assume that because there is more clients joined, actually is quite hard to tell the problems. So, but as you can see, the objective function pointing and best-ending pointing, you can see more in the performance differences like 98 or 99 or 97 to 99. So, but our specifier can perform the best in these scenarios. And so that is a balanced data set, but here we are talking about the unbalanced data set. That's we implemented in Word. We evaluated in incomplete graph with 5 clients, 1 adversary. So you can see that we test with objective function points and best-ending attack. As you can see, that this the learning curve is not really stable because it is not imbalanced data set. So we also apply our data rebalancer to it. Then, but still, we can find the red line, which is our method that can have the better F1 score, and then the lowest false positive rate and false negative rate. Okay, we also evaluate with the computational burden. So you can see that momentum FA is the momentum with without the robustness, and here is with the full method. We can see that the time we need to compute the algorithm is actually smaller than the other baselines. Sorry, so I may have exceeded some time, so I would like to wrap up this presentation. So what we have done in ARCADIAN-IoT is we have rebalance the non-ID and imbalanced data for FL, and we also propose a communication efficient and robust federal learning aggregation rule. And this aggregation rule has actually outperformed the other state-of-the-art baselines, and we actually have performed this in the random network topology with multiple adversaries and with multiple clients. So for future work, we would like to explore more in the privacy attacks, such as membership inference attack. I have been mentioned previously, and for the future, we also want to integrate with cyber threat intelligence. That is will be talk more in the following sections. Yeah. So thank you very much for your attention.